Okay, so let's start. Lecture 1 is about binomial coefficients. Okay, so we will start with some combinatorics, and combinatorics is about numbers. And since combinatorics is about numbers, of course, in combinatorics we will try to prove a lot of formulas for different numbers, counting something, counting some objects, and so on. So how to prove formulas between numbers? So there is a fundamental idea. When two numbers are equal, what that means? So let's suppose we have number n and number m, and these are just some numbers. And what it means that n is equal to m. So, of course, that's kind of a very silly question, but actually it's not that silly, because what a number is an abstract idea of a quantity, of some number of elements somewhere, some number of something, and mathematically speaking it's easy to say. So numbers are cardinalities of finite sets. So let me just emphasize this kind of philosophical idea. So numbers are cardinalities of finite sets. So every finite set has a cardinality, and very formally speaking, so one should say probably that if you have all finite sets, then some sets are in bijection with each other. This gives some equivalence relation between finite sets, and classes of equivalence are called numbers. I don't want to go into that because we will talk about these equivalence relations later on, but just for now, let me just emphasize that okay, numbers are cardinalities of finite set, and let's take a set A. So A is a set, and then we will denote by this thing its cardinality. And of course, very clearly, the cardinality of empty set is 0. And for any non-empty set, cardinality is greater or equal than 1. So then, between sets, there is a notion of a map between sets. So there is notion of a map from a set to another set. And there are a few different special kinds of maps, and when such maps exist, then there are important relations between cardinalities. So let me remind you. So when you just have a map, it means you have a set, and you know where each element of the first set goes. And then there are three important definitions. So F is injective if for every x1 and x2 inside A, if f of x1 equals to f of x2, then x1 equals to x2. So injective map is a map which sends different elements to different elements. And this one is an example of a map which fails to be injective, because two elements go to the same. So if there exists an injective map f from A to B, then it's really easy to show, and I'm not going to do that. Cardinality of A is less or equal than cardinality of B. You can think of that as just thinking that the image of F is basically a subset of B, and this is a subset, it has less or equal number of elements. I'm not going here into any fundamentals about set theory. You probably have seen it during your calculus course, but since we will do a lot of these bijections, injections, rejections proofs, I want to remind you the basics. So also F is surjective if for every y in B there exists x in A such that f of x equals to y. So for every element here there is something where it came from, and this is an example of a not surjective map. And so then, so if there exists a surjective map f from x to y, sorry, from A to B, then cardinality of A is actually greater or equal than cardinality of B. That's also very easy to show. So finally, there is a notion of bijection. So F is bijective if and only if F is surjective and injective. So different elements go to different elements, and for every element in the other set there is somewhere where it came from. So such map also can be called a one-to-one correspondence between elements in B and elements in A. So there is a very important criteria which we will use 1,000,000 times when a map is a bijection. So F from A to B is a bijection if and only if there exists G from B to A, which is called the inverse. So a map which goes backwards, such that for every X in A, if you first go by F and then go by G, you will go backwards. And for every Y in B, if you first go by G and then go by F, then you are back. So you need to check both of these facts, and it's not sufficient to check just one. And then, so if this is true, then F is a bijection, and G is just denoted by F inverse. That's called the inverse map. So probably you know that very well. And of course, if so, cardinality of A equals cardinality of B if and only if there exists a bijection between A and B. So I will talk about finite sets here, but honestly everything makes sense here for infinite sets, and you can even define these cardinalities as basically classes of equivalence of bijective sets, but you should be slightly careful here with set theory. And then indeed, if you have an injective map, then you can call them that cardinality is less or equal. But then, for instance, proving that if there is an injective map from A to B and from B to A, then there is a bijection between two sets, that's pretty remarkable theorem. It's not very simple. And so I'm not going into this set theory issues and very interesting topics around infinite sets, but just beware of that. For us, everything here will be finite. Okay, so this is a bijection, and what else? Yeah, but what is very important here is that if you have two numbers and they are equal to each other, you kind of think that there is nothing exciting going on. Just, you know, 5 equal to 5. I mean, what interesting math do you have here? But actually, when you are looking at sets, and if you look at a set consisting of 1 to 5 numbers, so this is just a set of 5 integers, and another set of 1 to 5 integers, and you can imagine that these are, I don't know, giraffes and these are elephants or something, then the fact that 5 equal to 5 means that there is a bijection between these two sets. And what is remarkable is that this bijection is not unique. So though we kind of think that numbers are, you know, either equal or not, but when you actually look how they are equal, in which way you can identify one set of numbers with another, a set of elements with another, then you will find that there are different, like, many ways to do it. And this is already interesting, because now we can ask, okay, so suppose we have a finite set A and finite set B, and there is a bijection between them. How many bijections are there between them? And it is easier to think just about bijections from a set A to itself. So question is how many bijections from A to A are there? So this is some kind of a fundamental question about the universe. So if 5 equals to 5, how many different ways are there to identify 5 elements with 5 elements? Okay, so the answer to that is probably well known to you. So if cardinality of A is equal to n, then number of bijections is n factorial, meaning n times n minus 1 up to 1. So n factorial is a number of bijections from a set to itself. Okay, so of course one can go deeper. One can try to understand what properties bijections have and how they sort of talk to each other. Because if you think about some set, let's imagine a set of 10 elephants, and then bijection of the set to itself is just a way to permute this guy. So take one elephant, move it somewhere, exchange places between them, and so on. So one can think about bijections from a set to itself as just permutations of elements. And if you start to think how you can permute things, if you have done any maybe sorting in computer science or anything along these lines, you know that there is something interesting going on there. So there is some theory about it. For instance, you can just exchange two things, or you can move some subset of elements along a cycle, and so on. And this leads to one of the most fascinating objects in mathematics, symmetric group, which we will definitely study in some detail, and it will appear later. But let's not rush into that just yet. So I'm just emphasizing that already this question is extremely deep. But we are talking about combinatorics, so we are interested in this n factorial number. So the first very naive question one might ask is, okay, n factorial is exactly how big? Because it seems that it is growing pretty fast, but let's just, for some intuition, for later, maybe roughly estimate what n factorial is approximately equal to. So for that, of course, we need immediately to go to a completely different area of math. We need to leave all this elementary set theory and to use some analysis or something, because otherwise, how would you approach this problem? So I'm going to talk for the next several minutes about how we can give a very rough estimate of n factorial, and then we will start talking about binomial coefficients. Okay, so let's just think what n factorial is roughly equal to. So maybe a little, so firstly let me remind you, so 0 factorial is just put equal to 1 usually, that's just convention. And then 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and so on. And again, so we know that this is a number of bijections, and so this means that if you have 3 elements and 3 elements, then there are actually 6 ways to permute them. So if I denote them 1, 2, 3, 1, 2, 3, then let me just draw all 6 ways. So you can draw these bijections as some just maps, so you can use arrows. So this is one, this is another, and there is this one, and there is this one, and sorry, so 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and finally this one and this one. So I hope that already just when you just draw them in this way, you start to see that there is some interesting stuff going on. So for instance, you can try to see how many crossings are there between arrows and stuff like that, and this leads to interesting mathematics very fast. But we will talk about it later. So these are just some examples of permutations. So this is what this 3 factorial equal to 6 actually is about. So these are this 6 bijections from a set with 3 elements to itself. Perfect. Okay, so we continue with trying to estimate what n factorial roughly looks like. So probably you have an idea that this is a sequence of numbers which grows incredibly fast. And just to have some intuition of this combinatorial stuff, it helps to know how fast. So one thing which is really easy to see is that n factorial is less or equals than n power n. And indeed, it is just because it equals to 1 times 2 times 3 times n, and each of these numbers is less or equals than n. So that's why it's less or equals than n power n. And of course, this is a very rough estimate, so probably it's much smaller. But how much exactly? So to get some inequality from below, I want to show you a trick which you might know from calculus class. But if you don't, it's really important. Using integrals to prove estimates. And the actual reason why I want to do it is because I want to do as much interplay between areas as possible. So I want to show you how to kind of combinatorics talks with analysis. So for that, let's just, if n factorial grows very fast, let's take logarithm of it. So logarithm of n factorial is a sequence which is expected to grow much slower, and it equals to logarithm 1 plus dot 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 plus logarithm n. And this sum actually looks a little bit like a sum in the integral. So let's draw a graph of this function. So logarithm is a function which after 1 goes up very slowly. And then, so what is the sum of logarithms up to logarithm n? So this is just the sum of these values. And we want to estimate it from below. So let's draw little rectangles from n minus 1 to n. And then we see that logarithm 1 plus logarithm 2 plus and so on plus logarithm n is actually the sum of areas of rectangles. Let's say Si, where this is S1 up to Sn, just because each of them is 1 times logarithm. And then it means that logarithm 1 plus and so on plus logarithm n is actually greater or equal than integral from 1 up to n logarithm x dx. So this integral is easy to compute, so maybe, it's not the simplest one, but actually quite simple. So this one is this. And so the sum is nothing but n log n minus n, which is, so we want to compare it with another logarithm, and so we can say that it is logarithm of n divided by e power n. So that's cool. E appeared a bit unexpectedly, and so we eventually get that actually n factorial is less or equals than n power n, but greater or equals than n divided by e power n. That's pretty cool result. Of course, it's not very accurate, and what actually is true is something called Stirling formula. So Stirling formula, and it is a beautiful statement that limit when n goes to infinity n factorial divided by square root of 2 pi n over e power n goes to 1 is equal to 1. So that's even more beautiful because it has a square root of n and it has a square root of 2 pi. N over e comes from here basically, and it's not very hard to show. So square root of n can be seen if you just actually use slightly more careful trick with integration, but to see where square root of 2 pi comes from, that's a more elaborate task. So maybe we will prove it later, maybe not, I don't know yet. But what I want to emphasize is that when you start to look even at such naive and combinatorial problems as how many bijections from a set to itself you have, you very soon come across some beautiful mathematics. So, okay, so now let's forget this trick with analysis. So in homework there is a place where you will repeat it maybe. And what I want to do next is to explain what binomial coefficients are and how to prove things about them with bijections and with some other methods.